Hello students, welcome to Apna Tutor channel. In the last class we were discussing the applications of Gauss law, where we have discussed the point charge, long charged wire, infinite plane sheet and hollow charged sphere, which we also call it as uniformly charged spherical shell, since none of the charge will be distributed inside the sphere. So we can say this also, right? Now we are discussing the solid charge sphere or the non-conducting sphere. So the amount of charge will be distributed inside the sphere. Now we'll be having its rho. Rho means volume charge density, since the charge is distributed inside the sphere. And then we'll study the solid conducting cylinder and then non-conducting cylinder. Okay. So let's start with today's lecture with the application number 5. So it is non-conducting sphere. Now let us draw a sphere of radius, let it be r, and we have to find the first of all let us find the electric field outside the sphere. So outside the sphere we can write it as r greater than capital R. Now what will be our first step? It will be to draw a Gaussian sphere. So the Gaussian sphere will be spherical surface and let it be of radius small r, right? Now we have done our first step, that is we have drawn the Gaussian sphere. Now we will be writing the Gauss law. So the Gauss law is E dot ds is charge enclosed upon epsilon naught, right? So we have some charge distributed all over the sphere and it has some charge density, right? That is rho. So first of all we'll write in terms of rho, charge density, since we are given this, and then we'll discuss for the charge also. So we have to apply now Gauss law. So the Gauss law is written over here. Now we can substitute the values. So it will E dot ds E into 4 pi r square. So r will be small r, since we are writing this for the Gaussian sphere and the Gaussian sphere has small r radius. Okay, so that will be equal to charge enclosed. Now how much charge is enclosed in the sphere? Now we are given charge density, right? Not charge. Now we have to substitute in terms of charge density. So the volume charge density, we know that it is charge upon volume. So that volume of this sphere where the charge is distributed. So all of the charge is distributed in this original sphere. So we'll be writing the radius of the sphere where the charge is distributed. So this is the volume where the charge is distributed, right? So you have to keep in mind that here we'll be writing for the Gaussian surface and here the distribution of the charge. So it will be this charge enclosed will be rho into 4 by 3 pi r cube upon epsilon naught, right? Now we can cancel the terms. 4 pi we can cancel. So the electric field will be rho into r cube upon 3 epsilon naught r square. So we are finally getting the expression this for the electric field outside the sphere, which means that electric field is varying 1 by r square times. Okay, so this is the variation with the distance. So now if we are given the charge q instead of rho, so what will happen in that terms? Suppose we are given this q charge instead of rho. So what we'll be doing? We'll be applying Gauss law. Same our equation, this one changes to E into 4 pi r square. This is for the Gaussian sphere, so no change. Now the charge enclosed will be q, since it is inside the Gaussian sphere. So we are assuming that instead of rho we are given now whole q charge. So we'll be writing q upon epsilon naught So now we'll be getting q upon 1 by 4 pi epsilon naught r square, and this is a very well known expression, you have seen many times. So it is showing the property of the point charge. Okay, that expression was in charge density terms. Now we have written it in charge terms. Let's do for the inside. Now for the inside the sphere, for inside, that is r less than capital R. So again we'll be having a sphere, and now our spherical Gaussian sphere will be inside. So this is our capital R, and this is rho, and this let we to be here the Gaussian sphere. Okay, so it has the small r radius. Now again we have to apply the Gauss law. Gauss law says that integral, closed integral E dot dA or E dot ds is equal to charge enclosed upon epsilon naught. So E into Gaussian sphere 4 pi r square is charge enclosed. We have seen that enclosed earlier the whole charge density was enclosed. Now the enclosed charge density is this much only, so we have to consider only this much. For this what we will be doing is, so now again we will be writing rho equals to q upon the amount of charge enclosed in this Gaussian sphere. We have to see that only. So the volume will be taking now for this Gaussian sphere, so it will be 4 by 3 pi r cube. So you have to again keep in mind that the Gaussian sphere matters for the charge density too. Since for outside the shell the whole charge was distributed in capital R radius, so we took the value capital R. Now we have to see the charge distribution in this much of area or this much of volume. So for that we'll be using small r, right? So we have to write the charge enclosed, and that will be equal to rho into 4 by 3 pi small r cube upon epsilon naught. We have substituted this charge enclosed value. So again 4 pi will be cancelled out. Now we are left with electric field is equal to r will also be cancelled. So we are left with rho r upon 3 epsilon naught. So this is our expression for the electric field inside the spherical shell. Sorry, inside the sphere. It will not be shell since the charge is enclosed in the sphere, right? Now what is the important point to note over here, that for inside our electric field is varying directly proportional, okay, for r less than capital R, and for outside it was 1 by r square, right? So we can draw the graph for this. For inside, if I need to talk about, we have to see the variation electric field versus distance. So at r equal to capital R, below r equal to capital R means r is less than r capital R. So there we can see that there is a direct proportionality. So our graph will be a straight line, and for r greater than capital R, that is outside, it will be inversely proportional. So inside the electric field will increase and then it will be decreasing. Okay. Now what if we have to write this electric field again in terms of charge, not in terms of charge density? So here the charge density is enclosing the whole charge. So we'll be writing the charge density will be, now remember, now we are given the charge, so that will be that we will consider q. So it will be q upon 4 by 3 pi r cube, capital R. Now since the charge is distributed over the sphere, all over the sphere, okay, so we'll be writing it in this way into r by 3 epsilon naught. Okay, so we can cancel out this 3. Yes, so we are left with I can write it. So we are left with q r upon 4 pi epsilon naught r cube. So this will be the electric field inside the sphere. Okay, so this is our another expression. We can express it in either charge density terms or in terms of charge, right? Now let's solve for solid conducting cylinder. Also we can say that hollow cylinder, since the charge will be distributed only over the surface of the cylinder. Okay, so either we can have the name hollow cylinder or solid conducting cylinder. Now let me draw a solid hollow cylinder. Let it be of this shape, right? And this be the axis of the cylinder. Okay, so as it is hollow cylinder, so the whole charge will be on the surface of the cylinder. Let the positive charge be distributed on the surface. Okay, so this is how this charge cylinder looks like. Now I have to find the electric field inside and outside the cylinder. For that, since it is hollow, and we'll be seeing that the variation inside and outside, how electric field is varying with the distance. Okay, so as I have told you earlier, for the cylinder or the wire, the Gaussian sphere is just as the cylinder. So let me draw the Gaussian sphere for the inside. Okay, so let it be the Gaussian sphere, and this is the radius r, and let the Gaussian sphere be of radius small r. So I have to first calculate inside the cylinder, not the sphere. So for inside the cylinder, we'll be seeing that this positive charge has the electric field which is radiating outwards from both the sides. And again we can draw the three surfaces. So the first surface will be, let it be surface 1, and let this curved surface be 2, and let it be 3. So as we have discussed earlier, since the area vector will be outward normal, so area vector will be outward normal in this way, and the electric field is in this direction, so the angle is 90 degree. Therefore for this surface, flux will be 0, and similarly for the third surface, flux will again be 0. So we have to calculate the flux for the second. So we can write the flux equals to E dot dA for the third sphere, third cylinder, sorry, and that will be equal to charge enclosed upon epsilon naught. So for the left side we need to write for the second sphere, right? For first and second it was 0, and since it is a hollow cylinder, we'll be seeing that the Gaussian surface will enclose no charge, so the flux will be 0 for this case. Okay, so now again we have to find for the non-conducting solid cylinder. Means now the charge density or the charge is distributed inside the cylinder, right? So first of all, if we have to calculate at inside, for inside, that is r less than capital R. Here it is capital R, and our Gaussian surface will inside, let it be in this way. Okay, so now we must recall all the steps. It is just the case of steps only. First we have to write the Gaussian surface, and then we have to apply the Gauss law, and we have to check whether it is hollow or non-conducting, okay, solid. So then our method will split into two types. For the hollow, we'll be solving in a bit different way, but the steps will be almost same. And for the solid, we'll be including the charge inside the Gaussian surface. Okay, so these are the main steps which will be used in every system, right? Now let's solve for inside, where for the Gaussian surface radius is smaller. Let's apply the Gauss law, and as we have seen that for the surface 1, 2, and for this third surface. Okay, so the electric field we have to calculate only for the curved surface, that is phi 2. Since we know that for it will be, again the angle will be same, that is 90 degrees, so it will be 0. Now for that we will be applying E dot dA or ds equals to charge enclosed upon epsilon naught, right? So it will be E into 2 pi r l. So now it is equal to charge enclosed. So the overall whole charge density it is given that it is rho. But for the Gaussian surface inside the charge enclosed, if we have to see what it will be. Now for the charge density inside the Gaussian surface, so we know that rho is the volume charge density. Since it has charge inside, so we'll be using volume charge density, right? That is equal to charge upon volume of the small cylinder is pi r square l. So we'll be substituting this much charges enclosed over here, so it will be rho into pi r square l upon epsilon naught. Now we can cancel the terms, so these all will be cancelled and we are left with electric field inside will be rho r upon 2 epsilon naught. Okay, so this expression seems to be similar with the solid non-conducting sphere where it was rho r upon 3 epsilon naught for that, right? So in this case it is almost similar. So again we can conclude from this that for inside electric field is directly proportional to small r. Now let's solve for the outside cylinder. For the outside, now again our steps will be same. So the charge density is distributed inside and we have to draw the Gaussian sphere, Gaussian cylinder. So it will be of such case, right? Again we have to define that it is of small r and it is of capital R. So our first step is done, Gaussian surface, and then we have to apply the Gauss law on the first, second and the third surface. Again this is the same common step which we are doing. So for the first and third, again it will be 1 equal to 3 equal to 0. Okay, so for the second surface it will be curved surface and it will be E dot dA will be 2 pi r l. Okay, so now it will be charge enclosed upon epsilon naught. Now the charge enclosed is, as we know that it is volume charge density is equal to in charge upon 4 by 3, or for the cylinder part we know the volume is pi r square into l. So why now I am writing capital R? Since the charge is enclosed over this capital R region. Okay, there is no charge over this region, so we'll be writing capital R. You have to note that for the inside and for the outside, this is a major difference. I am highlighting it again and again. So it will be E into 2 pi r l equals to rho into pi r square l upon epsilon naught, right? So we can cancel out pi and l from here and we are left with electric field is equal to rho r square upon 2 epsilon naught r. So here we can see that electric field is inversely proportional to 1 by r. So if we need to draw the graph for this, so the graph will be for r less than, we have seen the relation for r less than capital R, it is directly proportional, and for r greater than capital R it is inversely proportional to 1 by r, while in case of solid non-conducting sphere it was 1 by r square. Okay, so this is the main difference. This is directly proportional between these two. So you have to keep in mind these expressions or otherwise practice for these. Okay, so in this lecture we'll study till here, and we'll continue with the next topic or in the next lecture. Okay, thank you all.